Swayam Prabha. Digital India. Educated India.
See, I want to mention something that was used in the proof of the four-vertex theorem, the differential geometric proof. So, we have this, we have this proof of Osserman, all right, and the only differential geometry that you use there is that you have to understand the use of the signed curvature. That is important. And the other fact that we used was, you see, the idea of the proof was that we started with this curve gamma, and it is a simple closed smooth curve. It's not necessarily convex. Okay, of course, in the convex case we have Syamadas Mukhopadhyay's proof, okay, which we have done. But if it is in the non-convex case, this is the Osserman's proof. And the essence of the proof is that you have to look at the smallest circle that encloses the curve. So you see, the point about Osserman's proof was that you took this, you took this curve gamma, okay, and you looked at the smallest circle which contains gamma. And then there are a couple of facts. The first thing is that this smallest circle which contains gamma has to meet gamma, okay, and the points of intersection cannot lie, all of them cannot lie in an open semicircle, okay, and therefore as a result, you see, you will have at least 2 points in the points of intersection of this curve gamma with the smallest enclosing circle, okay, and that is because if there is only one point of intersection, it is obviously in an open semicircle, okay, and that is not allowed, okay. Then we had this, then we made this statement that if you take 2 points where the smallest circle that contains gamma, which is C, intersects gamma, such as P0 and P1, okay, then of course at P0 and P1, the sign curvature of gamma is going to be greater than or equal to the curvature of the enclosing circle, okay. So k gamma is greater than or equal to k here, and k gamma is also greater than or equal to k here, where k sub gamma is the sign curvature, okay, and k is the curvature of that enclosing circle. It is a reciprocal of the radius, and it's taken as positive, assuming that you are traversing the circle in the anticlockwise sense, okay. Then the important claim is that there is a point in between these two consecutive points P0 and P1. There is a point in between in the segment of the curve between P0 and P1, such as Q1, where the curvature of the sign curvature of gamma will be strictly less than k, okay. So basically the statement is that you take any 2 points, consecutive points, where gamma hits the enclosing circle. There, of course, the curvature of gamma is greater than or equal to the curvature of the enclosing circle, okay. Then there is a point in between them on gamma, such as Q1 in this picture, where the curvature is strictly less than k, okay. And this requires an argument which is as follows. I mean, it is geometrically evident but we can give an argument like this. So let me explain that argument. It's a little bit of geometry. So the picture is like this. You have this circle. Okay, this is the circle C, which is the enclosing circle, smallest enclosing circle for gamma. And then there are these 2 points. Let me call them as P0 and so let me in general call them as P Pi and Pi plus 1. Okay, and these are 2 consecutive points where the where gamma touches the enclosing circle. Okay, so this is your this is your gamma if you want, a portion of gamma near Pi, and this is a portion of gamma near Pi plus 1. Okay, and in both of these cases, in both of these cases, what is happening is that, so at this point also, you see the curvature of gamma, the sine curvature of gamma is at Pi. So this is greater than or equal to the curvature of the circle, which is of course 1 by the radius of the circle. So this is, so you see, this is the center of the circle, O, O if you want, and this is the radius. Okay, so at this point also it happens, and at this point also the sine curvature of gamma at Pi plus 1 is also greater than or equal to Kc. Okay, and the claim is that there is somewhere in between, if you imagine the curve has to is wiggling, and somewhere in between there is a point here, say Q. Okay, so the claim is there exists Q in between Pi and Pi plus 1. So if I want to really label it correctly, so that I am moving in the let us say positive sense, then let me change these labels. So I will call this as Pi, and this is Pi plus 1, and I am moving like this along the curve, and along the circle I am moving like this. Okay, so this is going to be Pi plus 1, and this is going to be Pi. Okay, and the point is the claim is that there is a Q. There is a Qi if you want in between Pi and Pi plus 1, such that the gamma, if you take the sine curvature of gamma at Qi, the claim is that it is strictly less than K sub C. Okay, so basically the statement is that as you move from, see, at Pi the sine curvature is greater than or equal to Kc, at Pi plus 1 also it is greater than or equal to Kc, somewhere in the middle it is going to be strictly less than Kc. Okay, so between any 2 points where the curve hits the enclosing circle, and mind you, where it hits the enclosing circle should be a touching point. Okay, it cannot be a crossing point, because the circle is the smallest enclosing circle, and between any 2 such points there is a Q where the sine curvature is strictly less than that of the curvature of the enclosing circle. Okay, yeah, so this is the proof of the four-vertex theorem in the the non-convex case. Okay, in the convex case we gave the proof using the the Frane-Serre relation. Okay, but this is the non-convex case. So so you see, we have to show the existence of such a point. Okay, and the existence of such a point was used. Okay, and the net effect of all this is that if the points Pi, there are n of them, namely the number of points where gamma hits the enclosing circle, suppose there are n of them, then in between n of these you will have n more of the corresponding Qs, points which correspond to such Qs, and so you get 2n of them. Now these P's and Q's can be replaced by local maxima and minima for the curvature function. Okay, because what is happening is as you move from let us say from say pi to pi plus 1, at pi and at pi plus 1 the curvature is greater than or equal to the curvature of the enclosing circle, but somewhere in between it is going down. It is becoming strictly less than the curvature of the enclosing circle. Okay, that means there is certainly there is a local minimum there in between pi and pi plus 1. Okay, similarly if you take between qi and qi plus 1, there will be certainly a local maximum. Therefore, between any two successive points where gamma meets the circle, there is always a local minimum, and between any two such local minimums there is a local maximum. So on the whole you will get at least 2 n vertices. Okay, and the point is that there are at least 2 points in the intersection of gamma with C. Okay, it cannot be 1 point because all the points cannot lie in an open semicircle, and 1 point of course certainly lies in an open semicircle. So there are at least 2 points. So that means there are at least 2 such P's, and that means there are at least 4 such points where you have 2 local maxima and 2 local minima, and that is exactly the claim of the four-vertex theorem. So what is critical is to show that there is such a point such as Q. Okay, and the way to arrive at this point is that what you do is, it's a geometric argument. So the argument is that you again take the circle, and then so let me draw this pi. So pi here and pi plus 1 here. The first thing that we must notice is that both pi and pi plus 1 will lie to one side of a diameter. See, you take a closed semicircle from pi onwards along the direction of traversal of the curve. That means you have this pi, and then you have its antipodal point. So I will call it as pi op. This pi op is exactly the antipodal point, which is the point at the other end of the diameter passing through pi. Okay, then you see this pi and this pi plus 1 has to be within this this closed semicircle. Okay, and in fact so this pi plus 1 cannot go to the other side. Okay, because if it did, then all the remaining p's are also contained in between pi and pi plus 1, and then all the intersection points of the curve with gamma will be contained in an open semicircle. That is not allowed. Okay, so you take pi and you take the antipodal point pi opposite. Then if in this semicircle from pi to pi opposite, this pi plus 1 has to lie there. Okay, and the argument for that is that if pi plus 1 is beyond this point pi opposite, okay, then what will happen is that pi and pi plus 1 will now lie in an open arc of a semicircle, and all the other points are also between them in the way we are traversing. That means all the points of gamma intersection C lie in an open semicircle, and that is not allowed. Okay, so that is something that we have already seen. All right, therefore you see if you traverse from pi to pi plus 1, you have this semicircle, and pi plus 1 is somewhere here. All right, pi plus 1 will be caught between pi and pi op, the antipodal point. Okay, and now you see, the picture is that you have so this is a pictorial proof, but of course there is some geometry that is used. Okay, and so it is kind of more of what is called a synthetic proof. So you see, you have the curve. You can picture the curve like this. So this is your gamma here, entering, touching at pi plus 1 and then leaving. And then I can also picture a portion of gamma like this here. So entering and touching at pi and then leaving. Okay. Now, therefore, what you can see is that what I want to consider is this chord. Okay, look at this chord that joins pi and pi plus 1, and look at the portion of the arc of the circle, the enclosing circle from pi to pi plus 1, to one side of this chord, to the right side of the chord in this picture. Okay, and then you see the thing is that there is always a point q dash on the right side. Okay. So of course you could have taken q dash here where the chord, where gamma enters this portion and just before it touches pi plus 1, or you could have taken q dash here also where gamma is leaving pi. So you could have, you could have chosen q prime here or here also, doesn't matter. Now what you do is that here is the important construction. The fact is that without drawing pictures, there is a q prime on the right side of this this chord joining pi and pi plus 1. That is something that is that you cannot contest. That is obvious because at pi plus 1 and at pi the curve gamma is touching the curve C. Okay, so the curve has to enter on one side and then touch and leave the other side. So there are points of the curve on both sides. So you can find such a point such as Q. But now comes the important thing. Given any such point Q, what you do is that you draw this circle passing through pi plus 1, q prime and pi. Okay. And mind you, this q prime has been chosen, take care to choose the q prime not to be on the chord joining pi and pi plus 1. Okay. That you take care of. All right. Such a point should exist. All right. Now, the thing that you have to notice is that since the points pi plus 1, q prime and pi, since they are all not collinear, they pass through a unique circle. And if you draw that circle, you see you will get a rather large circle like this. You will get a large circle, and it's kind of, my picture is kind of bad, so better to let me try drawing it again. So I'll get a circle like this. Okay, I'll get a large circle like this. Okay, so I get so I get this circle C dash, and you can see that so the radius of curvature of C dash is certainly greater than the radius of curvature of C. Okay, that's because the point Q prime is caught between this chord and the portion of the circle C dash C. So incidentally, this is C. This is C. Okay, and therefore the radius of C dash is greater than the radius of C, and what this will tell you is that therefore the sine curvature of C dash is strictly less than the sine curvature of C. Okay, now what you do is that you see now you have this perpendicular direction. So let me show it like this. So there is this perpendicular direction here. Okay, and you start moving this purple circle C dash in the perpendicular direction towards the chord. Then what is going to happen is that you are again going to reach some last point on gamma which hits C dash. So finally, you will get a portion of gamma like this. Okay, so there is this gamma moving inside, it's wiggling about, and there is some final point, let me not draw it very symmetric. So let me draw something like this. Okay, so here is gamma going in. Then there is, this point here, which is the farthest point that you will get, where C prime will hit, gamma. If you translate C prime along this perpendicular to this chord, okay, towards the center. So finally, after you translate it to get such an extremal point, it will look like this. So basically, you will get, again, you will get this. Okay, so this is also, so this thing is, C prime translated. Okay, to touch gamma at, so that is your point, Qi. So this point here is your Qi. Okay, so that is the farthest point, and there is such a farthest point where it will hit. Okay, and then what you should notice at this point, so the way I have drawn the picture is, at this point what will happen if you look at this. See, either your translated C prime, this is translated C prime will be like this, and your portion of gamma may be like this. Okay, all right, it may be like this. In this case, you can see that so this is your Qi, and you can see that the radius of curvature of gamma at Qi is certainly greater than the radius of curvature of C prime. So it means, greater than or equal to, let me say, and therefore you see the sign curvature of gamma at Qi is less than or equal to the sign curvature of C prime, and that is strictly less than Kc. Okay. The other possibility is that it could also be like this. So what you could have had is something like this. You could have this kind of a case where, if this is the translated C prime, then you could have had a bump like this. So here this is gamma, here also this is gamma, and this is your Qi. And in this case, you see the sign curvature of gamma at Qi is actually negative, and is certainly lesser than Kc prime. Okay, and remember that Kc prime is strictly less than Kc. Therefore, the moral of the story is, in either case, you see you get a point Qi such that K gamma at Qi is less than strictly less than Kc in any case. So moral of the story is, between these 2 points, consecutive points Pi and Pi plus 1, where K gamma, the sign curvature of gamma, is greater than Kc, there is greater than or equal to Kc. Okay, there is a point where it is strictly less than Kc in between, and this is a crucial fact that is used in the rest of the proof. The rest of the proof is essentially that now between there are, let us say, n such p's where gamma hits the enclosing circle C, and mind you that n is at least 2. Okay, and then between any 2 p's there is a q, so you will also get n such q's. So basically, if you put the p's and 2 q's together, you will get 2n of them, and between any 2 p's there is going to be a local minimum for the curvature, and between any such q's, two such consecutive q's, there is going to be a local maximum for the curvature of gamma, and therefore you are going to get 2n points which are alternately local maxima and minima for the sign curvature of gamma. So there are at least 2n vertices, and n is at least 2, so it is the number of vertices is at least 4. Okay, so that is a proof, that is a geometric proof. The only serious differential geometry that is being used is that you are using the sign curvature here. That is one thing. The second thing is, this geometric argument uses the fact that at every point you have unique tangent, and that is guaranteed by simplicity. If the curve is not simple, a portion of it crosses itself, so at that point you will have more than one tangent. So you have an issue with fixing a unique tangent at any point. Okay, so this is the crucial ingredient in the proof, which I wanted to point out. Okay, so now, and of course I have, as I have told you, you see the full converse to the four-vertex theorem holds, and all you need is a continuous function which is equal at the endpoints of a closed interval, which is the same as a continuous function on a circle, if you want. Okay, and the important thing is that it should have at least 2 local maxima and 2 local minima. Then the theorem is that there is a simple closed curve, plane curve, for which the given function is the sine curvature function. Okay, and this converse is harder to prove. It involves more differential geometry. Okay, so I will go over to the next thing that I wanted to talk about. Okay, so the other thing I wanted to talk about is that I wanted to talk about see these involutes. One of the important applications of involutes are fabrication of involute gears. Okay, and I just want to say something that is probably of interest to especially mechanical engineers. Okay, but then it is kind of I only want to say the math part. Okay, the engineers will know the rest of it. Okay, so what is the math involved? So how are involutes used in involute gears? Okay, so important. So let me write it like this: important application of involutes, which is the involute gears. So you see the idea of gearing is that you have so you basically you have a gear with teeth, and then you have another one. So again, it's hard to draw a picture by hand, but let me assume that this is the center of a wheel of a gear, and let me draw a portion of the the disc which contains the teeth like this. Okay, and so there is another gear, let us say at another center, and again let me draw. So I have to draw something bigger. So my center is probably far away. Okay, and there are also again there are teeth like this. Okay, so the idea is that this is gear 1, and this is center 1, C1, and this is center 2, and this is gear 2. And of course the idea is that you see if this gear, let us say, turns like this, okay, then it will push this gear in this direction. Okay, and basically you want to transmit circular motion from one point to another point. Okay, in fact you want to transmit circular motion which is oriented along an axis to a different parallel axis in space. Okay, that is the simplest case. And so in this case, it is the circular motion of C2. The circular motion of gear 2, which is along the axis passing through C2, which is, if you want, think of it as a line perpendicular to the plane of the diagram through C2. It's being transmitted to a circular motion of gear 1, which is which has axis of rotation passing through C1 perpendicular to the plane of this picture. Okay, and of course you see it's obvious that if the movement of the second gear is anti-clockwise, and then the movement of the first gear will become clockwise. All right, so this is something that's physically clear. Now what is it that you want? So you see, when there is this when the teeth of the this is the tooth of the first gear. Okay, and it pushes against the tooth of the second gear. All right, there is this point of contact, and at that point of contact there is going to be a there's going to be an action like this. Okay, and see, in principle this action you see, the direction of the action need not be, perpendicular to the tangent at the point of contact. So basically what I'm trying to say is that, you see, at this point of contact, you draw the tangent, okay, and you look at the action of with which, the first gear, this tooth from gear, so in this case it's gear 2, is pushing down this tooth from gear 1. So you see the action may be like this, okay, and this angle in general, so this is the tangent, so it should not look like lambda. So this is the tangent. So this angle need not be 90 degrees. Okay. Now what you should understand is that so long as this angle is not 90 degrees, it means that this action has a component along the tangent. If this angle is 90, then it has no component along the tangent direction. And the moment you have component along the tangent direction, that means that there is going to be some tangential motion, and that will entail friction. It will entail some sliding and some friction, and that will be loss of energy and damage of physical parts. So basically the ideal situation is that you would like this angle to be 90 degrees. You would like the gears to be fashioned in such a way that wherever they touch, you see, the action is always perpendicular to the tangent at the point of contact. If that happens, at no point there is going to be a component of the action along the tangential direction. So there is literally, I mean, at least theoretically, there is zero tendency for friction. So that is the most ideal situation. Of course, in practical situations, if you look at it at a nanostructure level, then the surface will have irregularities, and there is going to be some amount of sliding, okay, and there's going to be some frictional loss, but that is going to be minimized at least. If you have enough technology to smooth out the surfaces at the nano level, okay, and do everything, okay, then you can get an ideal gear, okay. I do not know how far this is possible, but you can try to get as close as you want to that, okay. But at least mathematically, you must first have a theoretically accurate model which can do this. You need a profile for the gear for which this happens, at least in theory, for mathematics. Now that is where involutes come in. So what I want you to understand is that, you see, this what are the factors that affect these two gears? See, one factor is this, it is the distance between these two centers, okay. See that as you change the centers of the gears, okay, that also is going to have an impact, all right. Then the other important thing, and of course when you say the distance between the centers, that is also going to be equal to, if you want, the sum of the radii of the gears, okay. In some sense, if you take the maximal circles, if you take suitable circles, so somehow the distance between these two gears is one factor. Then also the radius of these two gears, if I call this as R2 and I call this as R1, okay, this radius also matters, okay. And then of course the shape of the gear teeth, that also matters. So there's so many things here, okay. So it would appear that if you fashion two gears for to be mounted at a certain distance, if you move the distance, if you move the gears further away or you bring them closer, then you see the profile has to be changed, okay. The profile curve needs to be changed, all right. And of course it also depends on the the number of the teeth, okay, the width of the teeth of the gear. There are so many involved things here, okay. But mathematically, how involutes help you is the following thing. So you see, what you do is that you essentially use involutes of a circle. So you do the following thing. You see, look at this situation where I have I have a circle C1. So here is a circle C1 centered at a point O1. Okay, and then I take another circle, let us say at some other point, O2, centered at some other point O2 and some other circle, and I don't care what is the radius of the other circle. So this is C2. Okay, and mind you, this radius is R2 and this radius is R1. Okay, now what you do is that you take involutes. So for the first circle, suppose I take a point here, and then if I draw an involute, so what I will get is I will get something like a spiral. Okay, and then similarly, if you take for the second circle, you draw the involutes, say taking say from a point here. So let me draw something here. Let me draw an involute so that it is going to touch this involute. Okay, this is the involute of the second circle. So you see, the involute is drawn by unwinding or winding a string on the circle. Okay, keeping a point fixed. All right. So this I1 is the involute of C1, and this is I2, and they meet at this point, which is, let us say, P, point of contact. Okay, now you see, by the very definition of involute, okay, see, you can see that so here is where my diagram is going to get messed up, so I think I'll have to draw it correctly so that I can convince you. So there is the first important thing that you should notice is that you take any point on the involute and you join it to the starting point. That will be normal to the involute, and that line will also be tangent to the original circle. Okay, so all I am trying to say is that if you join, let us say, so this diagram is not accurate, so let me do it one by one. So you see, you do the following thing. So I take this first circle O1, centered at O1. This is C1. Okay, and then I take this point here, and then I draw the involute from here. Okay, so if I draw this involute, okay, you know that you take any point on the involute P. Okay, you join it to so what should I say? Yeah. So you use the fact that you see at any point on the involute, you draw the normal. That will be the tangent to the original curve. See, the normals to the involute will be tangents to the original curve. So you see, if you start with a curve like this, gamma, okay, and then if suppose I take a point P here, and then I take a length of string here like this, okay, and I pull it out, okay, so my involute will be like this. You see, my involute will be like this. Okay, and you take any point on the involute, you see, you draw the normal to it. That will be tangent to gamma. Okay, because basically what you have done is you have pulled out you have pulled out, when you pull out a portion of a string, the point that you have pulled out is still at a minimum distance from the curve. Okay, and that should be the perpendicular distance. And as you pull it out, the point from the point you have pulled out to the point on the curve where the portion of the string is still stuck, that's still a tangent. Okay, so you see, therefore, moral of the story is that this will be a tangent, and this will be tangent to gamma, and at this will also be normal to the involute of gamma. Okay, so I'm using the fact that at any point of the involute, you draw the normal, that will be tangent to the curve. Okay, so the net effect is that I will get a I will get a tangent. If you draw this tangent, this will be normal. All right, and similarly, yeah, perhaps I should resort to some pictures that I have already drawn using some software. Otherwise, I'm going to be in trouble. But anyway, so I just want to say, even naively, okay, if you are not going to, I mean, you can draw the pictures accurately, but I want to use only one geometric property. You take any point on the involute, okay, and draw the normal to it. It's going to be tangent to the original curve. Okay. Now just imagine so you see this is a point on the involute, and this is the involute I1 for the circle C1, and there is a point on it, and the normal at that point is actually tangent to the first circle. Okay. Now you see the same argument applies to any involute of any other circle. See, this argument applies to any involute of any circle. So basically what you do is that if I just extend, so you do the following thing: you extend this you extend this line, okay, and now you draw another circle here with this as tangent, okay. And so this is my circle with center O2, radius R2. This is my circle C2. Okay. And then what will happen is that for this circle, if you draw an involute, okay, so that it hits at P. So what will happen is that, it will be, so, so how do I draw it? So I draw something like this. Okay. So this is the involute I2 of the circle C2, and for that also you see at the point P, this is still the normal, and you see this then becomes the common tangent to both circles. And what is interesting is, you see this O2, the circle C2 with center O2 and radius R2, there are literally infinitely many choices. I could have taken O2 and R2 as I wish. The only thing I have to make sure is that this line passing through P, that is a common tangent to both the circles. That is only restriction. But there is literally no restriction. So which means that I could have chosen O1 and O2 anywhere. The distance between the two circles, that is at my disposal. Also the radius R2 also is at my disposal. I can change it. Okay. The only condition is that this common T, this line has to be common tangent. Then what happens is that you draw any involute I1 to C1 in the right direction, and you draw any involute I2 to C2. Wherever they will meet, they will meet exactly, perpendicularly. So what will happen is at this point, okay, if you look at it. So if I draw the diagram more neatly, it's like this. Oops. So at this point, okay. What I want you to understand is that you see you can fix the circle C1, you can fix the circle C2 as you wish. That means you can fix the distance between their centers as you wish. You can also fix the radii as you wish. All these are, you can control them. The only condition is that this T should be the common tangent. And draw any such involute I1 and draw any such involute I2. Okay, wherever they meet, they will meet at a point only on the common tangent. And therefore, at that point, you see when these two surfaces of these two involutes hit, at that point the normal is exactly perpendicular to this line, okay, which is the common tangent to the two circles, and that means that the action of one on the other, it is going to be exactly perpendicular to the tangent at the point of contact. So you see what is going to happen is the tangent at the point of contact will be like this. So if I put something else, so the tangent at the point of contact will be this. Okay, and when suppose this is pushing, okay, then the action is going to be like this. And for the tangent at the point of contact, you see it is at 90 degrees. Therefore, there is no frictional, there is no component along the tangent at the point of contact to produce friction. And what is important here in this picture is this point P was arbitrary. So if you started moving, you see, if I started moving this, suppose I started moving it like this, then you see this, this I2 will start moving down like this, and it will push, I1 like this. Okay, and this, you can see that the point of contact will start moving upward. No. See, when you move this involute, it is like looking at a parallel involute. I mean, if you physically move it, after some time you will get a parallel involute if you consider the original curve. Okay, so there is some dynamics in this. So you see, so all I want to say is the following thing. Forget all that. Okay, it's impossible to explain this without a nice animated picture. Okay, but I want to say the following thing. What I want to say is that no matter how it touches, at every point you see there is no tangential component of the action. So there is zero friction. So it is the ideal, gearing profile. The involute of a circle is the ideal gearing profile. Okay, and what is important is that if you fashion out gears like this, okay, then it doesn't depend on the distance between the gears, the centers of the gears. It does not depend upon the size of the gears, the radii. Okay, and you get, the only thing you have to worry about is just make sure that the profile is the involute profile for the corresponding circle. That takes care of the fact that wherever the teeth of the gear, whenever the profiles touch, okay, they will only have a normal component. There is going to be no tangential component, so nothing that can contribute to friction. Okay, so that's a very, very important thing. Then the other thing is, you see, as they touch, since when one thing moves, rolls on the other, you see the distance, the arc length moved on one involute is the same as the arc length moved on the other involute. Okay, but the arc length moved on each involute is actually the angle by which the gear has turned times the radius. Therefore, what you get is a product of the angle turned by each gear into its radius. These products are equal because they both correspond to the same arc length by which the amount of arc length that has touched. Okay, so what you will get is that if the moral of the story is that if so let me use if there is a portion, see, suppose there is a portion of arc length S moved, okay, by this gear, all right, and it will happen that the same portion of arc length will also be moved by the corresponding touching points of the other gear. Okay, but you see, this S will be R1 theta 1, where R1 is this radius. It will also be equal to R2 theta 2. Okay, and therefore what you get is from this equation, if you think theta as function of time and differentiate, you will get R1 omega 1 is equal to R2 omega 2, where omega 1 is d theta 1 by dt and omega 2 is d theta 2 by dt. These are the angular velocities. So what you are getting is that you see the ratio of the angular velocities of the gears is constant. It is just the reciprocal of the ratio of the radii, which of course corresponds to the fact that the faster the gear moves, the smaller the radius of the gear. Okay, but this is the this is the fundamental requirement, fundamental law that has to be satisfied by gears. Okay, the ratio of angular momentum of the two gears during transmission, that should be a constant. Okay, so that condition is satisfied here. All right, and so the way all this is put to use is that what you do is you do the following thing. So this is the part that engineers do. So you take a circle like this, and then you start drawing spiral involutes. Okay, and then you draw involutes in the other direction. So you start drawing things like this. Okay, and then what you do is that you cut out a portion of this. So here you draw a circle like this, and you cut out this portion. So this is your tooth. So this is one tooth, and this is the next tooth, and this is the next tooth. Okay, and this is how you get the teeth of the gear. And the beautiful thing is both sides of the teeth are involutes of the circle. Okay, so the gear can work in both directions, and so you just have to do this. And you see the radius of the circle is at your control. Okay, and where you want to place the center of the gear is also at your control. You can simply do any two such gears and simply match them. Of course, you will need to adjust the thickness of the teeth of the gears carefully. But the point is, wherever they will touch, everything will be nice. I mean, wherever they will touch, the action component will never have a component along the tangential direction. So there is zero friction, at least theoretically. So that's how you make involute gears. Okay, so this is a very, very important application, and literally most of the mechanical gears are of this type. Okay, so that is about this. And then yeah, all right. So the other thing I wanted to say is about I wanted to say two more things. One was which I will do tomorrow anyway, not today. So one was I want to say something about the cycloid and the brachistochrone, tautochrone, and cycloidal pendulum problems, and which is connected also with the fact that cycloid is its own involute and evolute. And then finally, I want to give the Gauss-Bonnet at least for curved polygons in the plane. Okay, which is a kind of generalization of the Hopf-Umlauf sets, and that can be deduced from that pretty easily. Okay, so yeah, so and then I will we can call it a semester.